Hello everyone, welcome to another lecture of Python with Data Analytics with Python. In this lecture, I will discuss some basic matrix operation. As we are, as you are aware of, we are discussing linear algebra. I've already told that linear algebra is very important for not only the data analytics but every field of computer science, be it graph calculation, be it uh, animation, game programming, or even complex algorithm. For instance, Google page ranking algorithm is also based on the matrix operation. So you must master it. So matrix operation, I have already discussed that a few matrix operation using NumPy. NumPy are our basic tool to create ND array, n-dimensional array, and you know matrix is a two-dimensional array, so we can easily calculate, make a matrix using NumPy and the array. And also NumPy has a function, a class called matrix. So we can create matrix using ND array, simple and array function of matrix, and also we can create matrix using matrix class. So what is difference? There is minor difference, and you can basically you can use ND array instead of matrix class. It doesn't matter. Only the matrix class give you some readability, and you can write a neat code using that class. On the other hand, then you have to convert ND array into matrix, and again from matrix to ND array to do another calculation. So let's see how we quickly revise basic matrix operation. Import NumPy. This is our array. If you remember, a range, create the range from 0 to 6, 0 to 6, have its value 1, 2, 3, 4, 5, 6. And reshape into 2 into 3, that means 2 row and 3 column. Similarly, we have another two-dimensional array. These two are called matrix. Because it is two-dimensional array, it is naturally a matrix. I have already told that matrix can be also treated as a vector. If you remember the vector definition from the last lecture, you can see that the matrix fulfill all the criteria of the vector definition. So a matrix can be also treated as a vector. Any operation that we define on vector can be done using matrix. And another important thing of matrix is it acts as an operator on another vector. I will explain that to you later, because this is the most important thing. A vector will represent in n dimension any point. So for example, in our data, in n dimension we represent a data point by a vector. But how we do carry on some operation on that point? Simply by multiplying some matrix to that vector. A matrix transforms one vector into another vector. We will see it later. So the most important, as I have discussed, that in general vector, it is the dot product that defines the length and separation between angular separation between two vectors. So dot product is very important. We have defined two vectors using, or we have already done that, and I have already discussed this function dot np dot a into b. It is in fact the matrix multiplication. So there is a little confusion. We can carry on the same thing using np dot inner a b. Yeah, inner product. uh, if we use that is the difference, that np dot and inner product. If you remember my last lecture, I have already told that the inner product is a general term and dot product is a special type of inner product. Means almost they are similar, but inner product is little general, and dot product we basically define on the vector. But in numpy it is little confusing. Dot np dot represent matrix multiplication. Matrix multiplication is nothing inner product, but in inner product it is required that your both a and b should be of same length. For example, it is 2 into 3, and if I put is 2 into 3, now both are same length, right? So here the inner product gives a valid output. So what is difference between dot and inner? Inner product and dot product, if you read the documentation of dot product, basically it is also not the dot product, mathematical dot product of vector. Dot product in numpy has a meaning for, it's a different meaning for a different argument. If you put two vectors of equal dimension, it is simply dot product. But it can do if we put a and b of similar matrix, it is a matrix multiplication. But it can also accept a and b, the argument a and b of different dimension. For example, a can be 1 into n dimension and b can be n into 1, and their operations are different, they are carried in a different manner. So in numpy, dot product is np dot is little confusing, and so you must always remember this for its documentation. In every case it is calculated basically in different way. For example, in 1D array, that is our vector, simple vector, it is simply the inner product. It is inner product, right? If a and b are 1D array, it is an inner product. If a and b are 2D array of same matrix of same, if 2D array, both a and b have the same dimension, it is a matrix multiplication. So np dot is one method, you can use it for matrix multiplication, but np dot has a different meaning for another thing. For example, here it gives you inner product, and if either a or b is a scalar, simply it is a scalar multiplication element wise. But you can use numpy dot multiply for better. And if it has a different dimension, look, this last 2 point is little confusing. If a is ND array and b is 1D array, n into 1, okay, it is some product over the last axis of a and b, right? It is some product of the last axis of a and b. So first argument is ND array, means first argument of np dot is ND array, and the second argument of is 1D array, means already remember 1D and b is the smaller, then it is some product over the last axis of a and b. That means every element is multiplied and summed over. Now if it is opposite, if a is ND array and b is MD array, where m is greater than 2, here look, b is 1D array, means it is smaller, Here if B is MD array means it can be one array, but it can be more than one D array. But here M is greater, sorry, B is here B is greater, so M is greater than B. Yes, it is a sum product over the last axis of A and second to last axis of B. Always remember this, second to last axis of A and the second to last axis of B. This is a little confusing here. So actually the matrix, this dot behave as per the argument you supplied to, and it is little confusing. So dot product we can use for the inner product, NP dot we can use for the matrix multiplication. The last two is little confusing, so you must remember it and avoid using dot product. There is a nice operator if you are using from Python 3.6 or later. In Python 3.6 another matrix multiplication was Python is used so much for scientific computation that Python as a language introduced another operator, that is the matrix operator. So NP dot, if 2 into 3 into 3 into 2, it is simply the matrix multiplication, right? NP dot, and NP inner in this case will result an error. So NP inner, always remember both the matrix, both the argument must be of same dimension. It gives you the vector inner product. So if you have to calculate the vector inner product, always use NP inner function. It is less confusing. NP dot is more confusing, and avoid even for the matrix multiplication or even for the inner product. If you have only the last two case, then if you have to do only the last two case, then you use NP dot. But you will find NP dot very much in use, but avoid using it. So NP dot inner is simple our vector inner product, and we define, remember that we define the length of the vector using the inner product, and also separation between two vectors using the inner product in general vector. Okay. While in three-dimensional vector, that is the difference of linear algebra. In vector calculation in in three-dimensional space. In three-dimensional space, length and angle is more vivid, means more basic concept, and from that you calculate the inner product. But in more than 3 dimensions, we have this inner product as a basic concept, and the length and separation between two angles are defined in terms of inner product. So here is a nice operator, that is new infix matrix multiplication operator introduced in Python 3.6 or later. So if you have Python 3.6, this will work. And let's see, if A and B, it gives the multiplication. NP dot, look, NP dot, if I reverse it, it again also give you NP dot according to that fourth definition. You can use that. So here is the difference. I have you just work it out yourself. Read the documentation of NP dot and work it out yourself how this output is calculated. Here it is 3 into 3, so I have, and vector is 1. Look, A is 3 into 3 and x is 1 dimensional. So if I put x into 1, A, it will give is the second last option. So on the last axis, it will sum product over last axis. Okay, sum product over last axis. So what is the last axis? Last axis, here it is 0, 1, 2 and 0, 3, 6. Remember, this is the first axis and the last axis is, this is the first axis and last axis is this. So 0, 3, 6 multiplied by 0, 1, 2. This give you a 3 and 12, 15. 147 multiplied by again 0, 1, 2, and this give you 18, and 258 again multiplied by 0, 1, 258 again multiplied 0, 1, 2. And if you reverse it, it will give a different output. Here what happened? A is greater and x is lesser. Sorry, it is otherwise. The before, if I put a into x, then it is a has a greater dimension. It is the second. It is the last option. Let's see the documentation. P dot. Look. A is ND array, B is 1D array. It is the sum product over the last axis of A and B. So B is 1D array. In this case, here, yeah, it is the second last option. So it is a sum product over the last axis of this. Got? Yeah, I was right previously. It is the product of last axis. Yeah, in this case it is the second last. And if I put x into a, then this is the case. This gives you a second to the last. So x has this last axis 0, 1, 2, last axis 0, 1, and a second last. And second last is, so the element on the first axis is this matrix, okay, and element on the last axis is 0, 3, 6. That's why this is multiplied 0, 1, 2 multiplied by 0, 3, 6 and sum of. Got it? So here is why matrix, this dot product was introduced in the earlier version of NumPy. Now it is less used because if you calculate like this, for example, BA into B inverse. So using dot product, we have to give something like this. For inverse, we have this NP. Linear algebra has inverse this operation. So you can NP dot B, then we write this function B, again NP dot, recursively we are writing it. So this give you the result. So the better way is to write is like this. Again, if you are using, again it is using B dot as a method. Remember, dot, we are using dot as a function. We can dot is also defined as a method on ND array. So here dot as a method is used. It is also, it is little less complicated, but it is also complicated. And here look, with matrix operation, this become nice expression. So matrix basic multiplication, matrix data structure of NumPy, and that's why matrix data structure is used, because even with this dot product, this expression is quite complicated, and therefore earlier NumPy version has this matrix type, and it is defining using np dot matrix function. So here using matrix function, I am using here the matrix operation. Using matrix function, yeah. So with matrix type, this matrix function return the matrix type, and if you print it, you will see instead of array it is matrix here. So this matrix type support this operator, operator overloading. In general it is the multiplication, but here the type is matrix, so it means the matrix multiplication. So it looks nicer in this way, right? Using the matrix multiplication, same operation. But now as Python introduced this in-text matrix multiplication operator, we can write like this. Even with the ND array, we can carry out this thing. Okay. Also, matrix have few things like calculating inverse. Here, see, the inverse is calculated b dot I. It is implemented, this method I implemented on the matrix type. Here we are calculating inverse using this module np dot linear algebra dot inv. So that is related. If you are using ND array as a matrix, use for this function for calculating inverse. If you have matrix, then you can simply carry out using this. So it has but little disadvantage that you have to always to cast type ND array to matrix type, again matrix type to ND array. So it depends on your application or what will be your choice. Now power. Again, the NumPy linear algebra module has this matrix power. You can simply give matrix as a first argument and power as a second argument, and it will calculate the power. If the power is less, you can simply use this in-text matrix operator. Trace of matrix is calculated using simple np dot trace. Trace, what is trace? Sum of the diagonal element. Okay. And if it is transpose, is calculating simply by, okay, T is also supported on ND array, and you can see dot T array. If you multiply a matrix with its transpose, the resulting matrix is symmetry. Let's see, the symmetry is 1717 along the diagonal element. Now the most important thing is inverse and determinant. Now we are using this SciPy model. I have already told that SciPy in the scientific ecosystem, another important package is SciPy. It has all the collection of all the mathematical algorithm, and we will start using it now. So many NumPy np.linear algebra module has many linear algebra calculation, but if you are using the same calculation is also defined in the SciPy. If you are using SciPy, then use the SciPy operation. SciPy linear algebra for carrying out these operations, because it is more optimized. But the input is always in NumPy array. So NumPy is simply give you a important data structure. The algorithms are again in different packages. For the matrix scientific calculation, we have SciPy model. For the machine learning, we have scikit-learn. For the image processing, we have scikit-image. That's all. So NumPy gives you simply the data, most important data structure, and the array structure. Pandas give you another tabular data structure, that is data frame. So here inverse is simply calculated as we have imported scipy dot linear algebra. Scipy module has not only algorithm for linear algebra but also other, for example, optimization, um, even image calculation, signal module. There are many modules in the scipy. You can explore it yourself. So the scipy linear algebra has this imported as LA, and LA dot inverse, we calculated the inverse of the matrix. Simply it has similarly it has this LA dot determinant for calculating the determinant. And now this is the most important thing, to calculate the linear system of equation. Ax is equal to b, where A is a matrix. Remember, A is a matrix, x is a vector, column vector, and b is also a column vector. If you have to solve the three simultaneous linear equation, four simultaneous linear equation, or m number of simultaneous equation, you can simply calculate it very easily using this. The algorithmic part, I am not going to explain it how this algorithm is implemented. You will learn it in your discrete mathematics. Basically, it is Gaussian elimination method. If you have, or I don't know if you have already learned it, but this linear system equation Ax is equal to b, it is the most important equation. We carry out all the formulation. We frame our problem in this expression simply, and then solve this equation. So how will solve? A, remember, A is the matrix, X is a column vector, and B is a column vector. So you can interpret it like this: A is a matrix that acts on a vector X and change it into another vector B. This is the important thing. What I am saying is that X is a column vector, it is a one kind of vector. A is a matrix, that means A matrix act on a vector, and B is also vector and change into another vector B. So A acts as a transformation for the vector X, and it transforms X into a vector B. Remember this point. For example, if you have to rotate a point in 3 dimension is a vector of 3 elements. We multiply any matrix and it will rotate, it will give you another point, that is rotated version. So A is act as a transformation for the vector, operator for the vector. Always remember this. So it is very easily simple. Again, we define A, we define B, and it is LA dot solve. Simple function, LA dot solve. The first argument is matrix, the second argument is vector, and replace this vector. Now one thing important, if it gives the result in the same shape of B, for example, if the B is a column vector, here B is a row vector, B is a column vector, the result will be also a column vector. Again, if B is a matrix, the result will be also a matrix. Means for B a different kind. So here B, it gives you the x1. With this matrix operation, in this short lecture I have explained the basic matrix operation, and in the next I will go in detail of eigenvalue and SVD.